Welcome back to our NPTEL course on scanning electron ion probe microscopy in material characterization. We were discussing on the different modes of AFM operation. In that part, we have already discussed on the contact mode of AFM, which is a static AFM. Today, we will discuss on the dynamic mode of AFM operation, which is the non-contact or tapping mode of AFM. Among the three modes of AFM operation, contact mode operates in the repulsive force regime of the force distance curve, and the non-contact mode operates in the attractive force regime of the force distance curve, and the intermittent is in between them, or that is also called tapping mode of AFM. As discussed, in case of static AFM, the atomic AFM probe goes above the sample without being oscillated. On the other hand, in case of dynamic AFM, the cantilever or AFM probes oscillate above the sample. As the oscillation occurs, we have several parameters that will play role to the oscillation, that includes resonance frequency of the cantilever, the force constants of the cantilever, the quality factor of the cantilever, particularly first two depends on the cantilevers, and the third one depends on both cantilevers and the environment in which the cantilever operates, particularly in vacuum. The quality factor is very high, above thousands. So, the non-contact mode is preferred in the vacuum environment. We can also control the amplitude of the oscillation, that is called drive oscillation, and again we can measure what is being driven and what is being outcome of the amplitude oscillation due to different tip sample interaction. Driving frequency can be selected, and due to the oscillation we can measure the phase difference or phase shift, and that phase shift allows us to get phase imaging in the AFM. We can also measure the frequency shift because of this oscillation. It is given at a particular frequency, and the resultant frequency may shift towards lower or higher, and all those can provide us information useful to our measurement. As per the detection, in the dynamic mode of AFM is concerned, there are two primary mode of detection. One is frequency mode detection. In these cases, the resonance frequency, shift in the resonance frequency due to the tip sample interaction is measured. So, a particular our cantilever oscillate at one particular frequency at its resonance frequency, and once that cantilever or probe have a certain tip sample interaction, the frequency may shift to lower value or to higher value. So, by measuring how much shift occurs and to which direction shifts occurs, we can measure the tip sample interaction, and that can be used for creating the images. In second mode is called amplitude mode of detection, where the atomic probe oscillate with a particular amplitude, and now that amplitude may change when the tip sample gap changes. The oscillation amplitude varies when the tip sample distance or gap changed, and using that amplitude, by measuring that amplitude, we can measure the gap between tip and sample, and that gap between tip and sample tells us about the surface topology and can be used for creating the surface topology. In the non-contact mode of AFM, the probe does not contact or come close to the sample surface. Instead, the probe oscillates above the sample with a small amplitude. Remember, it is very important to note that it is small amplitude, about 1 nanometer above the surface, and it is in the attractive regime. Attractive regime means it is a certain distance away from the sample. The attractive regime comes here. This is our attractive regime, and tip, certainly it is the tip sample distance, x is the tip sample distance, and this is the force curve. And now it is quite away from each other, that is why we are saying it is a non-contact mode. And due to the attractive force, because it is attractive region, the attractive force between the tip surface atoms, the resonance frequency of the cantilever vibration shifts from its intrinsic value. Resonance frequency is directly related to our, like we know, is equal to k by m. Resonance frequency is directly related to the spring constants of the cantilever. As the vibration shifts, the resonance frequency shifts from its intrinsic value, then automatically the spring constant value will change. So, then the changed value is called effective spring constant, that is called effective spring constant, and that k is our original spring constant, what is the intrinsic spring constant, that is our k, and it shifts by a value called f prime, that is the force gradient. That force gradient is the gradient between the tip and sample. There is a force between the tip and sample, that is a force gradient. Due to the force gradient, the effective spring constants decreased. The strong interaction between tip sample surface, there will be smaller, there will be strong interaction. When there will be strong interaction, this value will be more, the force gradient will be more, and thereby the k effective will be smaller, and there is a shift of the resonance frequency. There is a shift of the resonance frequency. So, by measuring the resonance frequency shift, we can measure the tip sample interaction, whether interaction is strong and weak, and that can be used for creating the image of the surface. This is what done in non-contact mode. If we look at the force distance curve, the frequency shifts of the resonance certainly due to tip sample interaction, and that is proportional to the force gradient, and this happens only when the tip sample force is approximate as linear in the range of oscillation amplitude. With a particular range of oscillation amplitude, this tip sample force can be approximate as linear. Here, as you see, this is our attractive regime, and this is a smaller amplitude, this is our amplitude, this is our amplitude of oscillation amplitude. With a particular amplitude oscillation amplitude, particular range of oscillation amplitude, this graph, this force versus distance graph, or the spring constant z values is linear. So, the linear region can be, if the linear region can be used for tip sample force interaction. This is one of the important, and there is second important point criteria to be fulfilled, that tip sample force gradient should be much smaller than spring constant of the cantilever. The force gradient should be much smaller of this spring constant of the cantilever. Otherwise, the tip or this probe will directly go and touch to the sample, and this linear portion will not be observed. So, in the small amplitude limit, tip sample force is approximately linear or approximately linear within the range of an oscillation proportional to the minus k prime, where k prime is the force constant between the tip sample, like we have tip and we have sample. Now, one is here the spring, that is cantilever spring, and another there is a distance between tip and sample, there is a interaction, and it is also a type of spring here, because there is a force between tip and sample. There can be attraction, there can be repulsion when they come close to each other. So, this force constant can be written as k prime, and here the force constant or spring constant for the cantilever is k. So, the total effective force constant is the cantilever spring constant reduced by the tip sample force gradient, which is proportional to the k prime. And accordingly, using this principle, linear principle, we can see a frequency shift, and frequency shift is directly related to the effective spring constant, and that would help us to measure the surface or tip sample interaction, and tip sample interaction provides us the surface topology. Now, the frequency shifts in the non-contact mode. If the tip sample force gradient is greater than 0, the resonance frequency will shift to a lower value. Resonance frequency will shift to a lower value due to the attractive force between the tip and sample. So, frequency shifts occurs in the negative direction when there is attractive force between the tip and sample. On the other hand, the frequency will shift to a higher value or towards a positive sides if there is a repulsive force between the tip and sample. So, the frequency shift of the oscillation from its intrinsic value can tell us the interaction is strong or weak, and it is to be noted that this frequency shift monotonously changes when the tip sample distance changes in the attractive regime. So, in the attractive regime, this frequency shift changes monotonously, and thereby providing us the correct tip sample separation. By knowing the tip sample separation, we can create a 3-dimensional feature of the sample surface. However, when the tip come close to the sample means the repulsive regime, there is a instability occurs. So, they do not follow then linear, they do not the curve become not linear, the frequency shift become not linear, and thereby this frequency shift concept cannot be utilized when the tip goes close to the sample or to the repulsive regime of the sample force distance curve. Another is amplitude mode. Amplitude by measure, it is nothing but to measure the amplitude. As we have discussed, we oscillate the cantilever to a particular frequency, that is mostly at the resonance frequency of the cantilever. Now, if we let us say that frequency is omega, that frequency is omega naught, that is the resonance frequency of the cantilever, free cantilever. So, now due to the attractive force, this frequency shifts, intrinsic frequency shifts to a lower frequency. Now, we measure this frequency shift in the non-contact mode. However, if the cantilever frequency or cantilever is oscillated at a frequency little higher than the resonance frequency, which is higher than means greater than omega 0, where the slope is steep, Now, if we provide the oscillation frequency or the cantilever frequency little higher than omega 0, let us say this is omega 1, where the slope is steep, as you see there is a large amplitude change, and this change of amplitude gives the information about, because this is directly related to the frequency shift, this also gives about the information about the tip sample gap or tip sample distance. So, we can also maintain this constant amplitude by providing the oscillation frequency a little higher than resonance frequency, and then also by keeping the constant we can also measure the tip sample separation. In order to maintain the constant amplitude, the tip has to go up or sample has to come down, and in this way either by taking the tip upward or cantilever upwards, complete probe upward or the sample downwards, we can maintain a constant amplitude, and because tip is going upward or sample is going downward, by knowing the position of the probe or sample, we can create a 3-dimensional features. This is what is done in the amplitude mode of detection mode, in the which is applies in the non-contact mode. So, in the non-contact mode, as tip is far away from the sample, it do not touch the sample. Moreover, as we discussed, the tip oscillation occurs with a smaller amplitude. As it occurs with a smaller amplitude, the cantilever should have high spring constant. Otherwise, there is a chances that tip can get stuck to the sample surface. In order to avoid the probe to stick to the sample surface because of the small amplitude, a high spring constant cantilever should be used, and silicon probe is most suitable for this, because silicon probe have a higher resonance frequency. And the advantage of this force and this mode is that a small force is exerted on the sample surface. In the contact mode, the probe directly come in touch with the sample surface, therefore, force will be higher. On the other hand, as here a tip is much away from the sample surface, the force exerted on the sample surface is very small, in the range of around 10 to the power minus 12 Newton, very small force. And thus there is no question of damage to get occurred on the soft sample, if we want to study the soft sample. So, soft sample are preferred to be examined by non-contact mode instead of contact mode. And again, as I discussed before, as I mentioned before, this method is much suitable for cantilever with a high quality factor, and high quality factor also depends on the environment, and in the vacuum it is high, greater than thousands. So, it is more suitable. Disadvantages: lower lateral resolution, because here tip do not come in contact with sample surface, it is away. We are measuring the force above the sample, not directly at when the probe touching the sample, therefore, lateral resolution is poor. A slower scan speed to avoid contact with the fluid layer. AFM operates both inside the fluid or in any environments in the ambient condition, and in the ambient condition there is a chances that there is contamination of water on the surface of the sample, and it does chances that if we go the fast, at some places it may stick to the water or contact with the fluid layer on the surface. So, therefore, slow scan speed is used for non-contact mode, and if the tip touches the water layer or contamination layer, then capillary force and will also gives undesirable force component, masking the actual force of the surface. So, the main demerits of the non-contact mode is that the surface contamination under ambient condition do not allow to measure the actual surface properties. But advantage is that non-contact mode, you are exerting small force, therefore, you can use this mode non-contact mode for soft sample measurement. But disadvantage is due to surface contamination. So, then the third mode is called tapping mode AFM or intermittent contact mode of AFM measurements, and this mode is most widely used under ambient condition, because this mode takes the advantages of both contact and non-contact mode, but do not take away the disadvantages of the other two modes. So, intermittent contact mode is most suitable for wide range of sample, and it is most commonly used. In this mode, cantilever is oscillated with a large amplitude. Previously, in non-contact mode, it was oscillated with a small amplitude, but here it is oscillating with a large amplitude, ranging from large distance where there is a negligible tip sample interaction or no interaction. So, in the force versus distance curve, here there is no interaction, here there is attractive interaction, and here there is repulsive interaction. So, now it is the tip or probe has to go from this region to the repulsive region. It goes from negligible tip sample interaction deep into the repulsive regime. So, the tip has to be oscillated in the region where there is no force between the tip and sample to where there is a repulsive force between a tip sample. So, it has to be oscillated with a very large amplitude. Due to the large oscillation amplitude, linear approximation of the tip sample force is no longer valid, especially when the tip comes close to the repulsive region. So, that linear approximation that we have used in the frequency shift mode cannot be valid here. So, harmonic oscillator cannot be used here. The concept of frequency shift of the resonance curve cannot be applied in this mode, because they do not follow linear relationship here. So, in this mode or tapping mode, oscillating amplitude is large, about 50 nanometer, and cantilever is also a high force constant, greater than 50 Newton per meter, or about it certainly should be greater than 20 Newton per meter. As the name suggests, here tip makes an intermittent contact with the sample. It go touch the sample and go above. It go again touch the sample and come up. In this way, it will go with a large oscillation amplitude, touching the sample in periodically. It keeps on touching the sample periodically and measuring the interaction. So, when it goes on close to the repulsive regime, where about to touch the sample, there is all sort range of force exist. So, and thereby giving the information close to the sample. In this mode, a constant driving frequency is selected. And that driving frequency is very close to the resonance frequency of the free cantilever, or little lower than the resonance frequency of the cantilever, but not at the maximum slope that we were discussing in our frequency modulation mode of measurements. The measured signal is the amplitude. So, amplitude will keep on amplitude will change when there is a tip sample interaction. So, the signal is amplitude here, which provides the tip sample distance. In addition to that, it also gives the phase shift. In this mode, amplitude depends monotonously on the tip sample distance. So, amplitude keeps on changing monotonously as the tip sample distance changes. So, by measuring the amplitude at different location above the surface, we can know the tip sample gap, and thereby we can create a 3-dimensional image. To maintain the oscillation of the probe, the snap to contact must be prevented. It must be noted that the tip should not go and stuck to the sample surface. Thereby we use large oscillation amplitude. With a large oscillation amplitude, even the tip comes close to the sample surface, it has almost negligible chance to get stuck to the sample or snap to contact to happen. Snap to contact do not happen because of the larger oscillation amplitude. So, here you see the force distance curve with a large oscillation amplitude in the tapping mode or intermittent contact mode. So, it is going from a region where there is no tip sample interaction, or almost no interaction here, going to a region of the repulsive region very close to the tip sample surface. So, very large oscillation amplitude here, very large oscillation amplitude, and if we look at the total force curve, this is the red line going from here to here. It do not follow the linear it do not follow the linear relationship in this region. In this region particularly, it do not become linear, this red curve you see, because of giving an n-harmonic oscillator type of behavior, but the oscillation remains sinusoidal. The oscillation remains sinusoidal, but it do not follow the linear behavior of in the force distance curve. So, therefore, Thus, frequency shift concept cannot be utilized in this case. You see what happens when the sample of different height is come in contact or contact with the probe. Here two different average height is taken, and the tip in this mode oscillating above the sample surface. What you see here, when there is a larger distance, here the tip is at a constant height mode, feedback Z feedback is off. When tip is at constant height mode and it is oscillating above the surface, amplitude is larger when the tip sample distance is more, amplitude is larger. But when the tip sample distance is small, here in the middle portion, here tip sample distance is small, the amplitude is small, and this follows a monotonous relationship. The oscillation remains sinusoidal even it is strongly enharmonic potential close to the sample. Even though there is a strong enharmonic potential in the repulsive regime, but still it is the amplitude relation, the oscillation remains sinusoidal and amplitude changes which is proportional to the tip sample distance. And here we plot oscillation versus tip sample distance. Here is the tip sample distance. As you see, it is the probe is oscillating at its resonance frequency. There is a free oscillator, it is a particular amplitude. We can set that amplitude also, and then when it is oscillating here in the one position with a higher amplitude. As it come closer to the tip sample distance, here closer to this tip sample distance, and as the tip probe come closer to the sample surface, the oscillation amplitude decreases, and it is further decreases here when the tip comes to the repulsive regime or very close to the sample surface. So, by measuring this amplitude, we can create a we can measure the tip sample distance, and therefore, with that we can create a 3D imaging of the sample surface. Here is a schematic diagram, how it is done. Normally, the normal piezo applied attached to with a cantilever is not sufficient enough to oscillate with a larger frequency. Therefore, another piezo is connected here to provide the oscillation with a particular driving signal, and we have a particular driving frequency. And with that, the tip will oscillate above the surface and its position will change, and oscillation changes. We will measure the oscillation using the detector, and we will know how much amplitude is there, how much phase shift there, and that information will be given to a pre-amplifier and then lock-in amplifier, and here in lock-in amplifier that information will be converted to voltage signal. It will give both phase and resulting amplitude, and that is to be compared with the reference signal what is being given here, driving frequency. And by directly measuring the amplitude, we can create 3-dimensional image, or we can again give the feedback to make the amplitude remain fixed and mop the Z signal. We can also do opposite way, and in that process also we can create 3D image using this process, using this scheme of measurements. The major properties of and advantage of the tapping mode AFM are like this is an intermittent contact that allows to obtain high resolution. As I say, it takes the advantage of both contact mode and non-contact mode. Contact mode has advantage of providing high resolution image. Therefore, it can also be used to provide the high resolution image. Even on the soft sample, in case of contact mode, we cannot use the soft sample because tip will damage the sample surface, but here as the tip is going and touching periodically, and it is a vertical movements, it will not do any damage. Lateral force will not act there, because here tip is going in the vertical direction. In the other cases, tip is touching. When the tip touches the sample surface, there is a chances of bending of the tip because of lateral force or frictional force, and then image will distort and also damage will occur in the contact mode, and in this case tapping mode it does not happen. And second thing is that it allows correct measurement of the sample surface under ambient condition. Again, contact mode allows correct measurement under ambient condition because tip touches the sample, but in non-contact mode tip is away from the sample, and therefore there is a water layer or liquid layer on the surface. If there is a contaminants on the surface, we actually measure the properties of those contaminants or force due to those contaminants rather than actual surface force, and thus not getting the correct information of the actual sample surface. But here our tip is penetrating into the contaminants and touching, going to the repulsive regime, almost touching to the sample, or it is touching to the sample, and thereby we are actually probing the real sample surface or actual sample surface, and therefore it allows us to measure the correct sample properties or precise sample properties, unlike the cases of non-contact mode. In the amplitude detection mode, the cantilever is driven with a fixed frequency, which is at its resonant frequency of the free cantilever, and the oscillation amplitude and phase is measured using a lock-in amplifier and a feedback signal. In contrast to the contact mode, no frictional force sideways forces are exerted on the sample, minimizing damage to the soft sample. This is what is the advantage of tapping mode. So, in conclusion, the frequency shift of the resonance frequency due to the tip sample interaction can be used to in the non-contact mode if they follow the linear path, and that follow the linear path with a certain amplitude range, and that is in the attractive regime of the force distance curve, which is used in the non-contact mode. And the frequency shift is positive towards higher frequencies for the repulsive forces and negative for the attractive forces. Frequency shift is considered negative in the attractive forces. In the frequency modulation or frequency modulation detection, the amplitude can be kept constant and then can be used for getting the information of the sample surface. In the tapping mode of AFM operation, oscillating amplitude decreases linearly with decreasing the average tip sample distance, and therefore can be utilized for getting the surface topology. And an anharmonic tip sample force at the repulsive regime provides the existence of two vibrational modes with a low amplitude and high amplitude corresponding to the attractive and repulsive interaction respectively. And at the transition between these two modes occurs at a particular tip sample distance when scanning from when it is scanned from one material to other material. And unlike the contact mode, no sideways or lateral force affect the measuring of tapping mode, giving the correct without damaging the sample as occurred in the contact mode of AFM operation. These are the two reference books. Thank you.